We're live.
All right, everyone. Well, this is another Wolfram Institute Community Forum. I think it's maybe our fourth, fifth,
Fifth.
fifth. Yeah, okay. So, well, often our streams consist of our live science streams, where we essentially hold some um, meeting to discuss active research that we are currently undertaking. And so those meetings are obviously open to questions, but they have a preset agenda, and we're mostly just talking amongst ourselves and making it live. So that others can follow and engage in some way. But the purpose of these fora is just to set aside time to answer questions that you all have and to engage in a much more open manner. And so, for those watching live, you can post questions, you can ask follow-ups, ask as many questions as you like. We'll see how many we get to. But also on our Discord server, which you can access via our website if you're not part of the Discord server, and our website is just wolframinstitute.org. Um, the questions are regularly posted there too, and we like to kind of collect those and rather than just type up many responses, which we also do, set aside some time just to respond to those. And Carlos is usually pretty good about keeping track of interesting questions and kind of piling them together. I mean, if there's Carlos, if there are interesting questions that you think we should just dive into, we can do that. We also can summarize a little bit of what we've been doing over the past week if people want a kind of if people want some synopses from each of us.
I think that's
I don't
good.
really mind either way.
I would go for a quick synopsis
Yeah,
from
okay.
everyone of
Well,
us, and then
I mean, you guys are doing the research. I mean, I could say it, but you guys are now becoming, more deeply involved in your own research. You can probably summarize what you're doing quite well at this point. So, you know, Wukash, why don't you go? Why don't you go first?
Oh, I don't know if there's like anything constructive I can say at this point. Like, I've been reading about these Heke characters. For example, we had developed some methods for dealing with like ordinal functions.
Yes.
And in the case of the extension of rational numbers through
Yes.
the Dirichlet characters. But then you get this generalization to the extension of arbitrary number field, but then you need to deal with Heke characters. And yeah, and you need to change a couple of things. You cannot simply mod out by ideal because there are some issues, and I'm trying to understand everything.
Now, when do you use a Hecke character as opposed to um, a Dirichlet character or just a representation of the Frobenius element? This is still all in abelian class
Yeah,
field theory.
yes, Heke
Yeah.
characters, all everything is abelian case. I don't think we will quickly get to the non-abelian case as it involves dealing with all these Adele groups and everything. And yeah,
Well, we will, but just
but yeah,
not this
we
week.
will, but
Yeah, yeah.
yeah, I found some Sage packet to calculating with adults. But yeah, so you use Hecke characters when you extend, not when you don't extend rational numbers, but some extension of rational number. So yeah, so example, if you want to extend q adjoint square root of 2 by square root of 3 or whatever, then you need to study the q adjoint square root of 2 using Hecke characters.
You can't. Okay.
Like, what would it be
Would you?
like regular Dirichlet character in q adjoint root 2?
But I just want to clarify, like in the arts and case. By the way, this is probably mumbo jumbo from people who are just tuning in. Wukash is doing this thing. Wukash is studying
Like,
this thing
should,
called class field theory.
should we begin every community forum like at the beginning actually, or
Well, no, but we have to find some way to give
Yeah.
the elevator
Maybe summarize.
pitch, talking to your uncle version of this research. So, Wukash is studying this thing called class field theory, which in essence is about the study of factorization of numbers within different number systems, basically. Sometimes you can factor numbers in a unique way. Sometimes there are multiple ways in which you can factor numbers, and class field theory is all about trying to understand when you can do one and when you can do the other. And there's been all kinds of more efficient machinery for doing that for different number fields. And Wukash has been diving into that. So the first thing he did was these art and L functions, which is this it's called analytic way of working through these, where actually Wukash just produced some nice images where you actually show the behavior of these number fields, which are these particular kinds of number systems on a complex plane. So you're basically doing complex analysis to study behavior of numbers. It's called analytic number theory, which is quite nice. But these particular functions are very similar to these things called this was a function developed by Artin, who actually is now considering something similar by this guy called Hecke, just trying to understand the relationship between the two. But we're also critically trying to understand this key theorem in class field theory, which I don't still fully understand. And it's by this guy called Takagi, which was eventually proved by Artin. And it seems like it makes class field theory much more efficient because it allows you to basically just do everything with number fields and field extensions and this thing called Galois theory. But we're still figuring that. Lukasz, have you figured the Takagi thing out yet? I saw that you shared a link with me. You still haven't figured it out. It's I'm developing some very loose intuition behind why I think it works, but still not quite. Still not quite.
Yeah, but that's kind of how it works. You just read and you don't understand nothing. And
it's not my standard. I mean, yeah, there's that von Neumann quote, like you never understand anything in math, you just get used to it. But I don't know. I find this with real mathematicians, with like professional, like people who just do math all day, is that they are familiar with everything. They can do everything comfortably. But if you poke certain areas, they've kind of just learned it, and they're like, okay, we can probably just get away with kind of just knowing the theorem and building from there. I actually want to understand it. So yeah, we're trying to understand this particular thing in class field theory.
Right. Nick, do you want to go next? Should I go next?
Oh, I can go. Well, yeah.
Sure.
Well, I kind of stepped aside from research for a moment just to code some functions and functionality. Like, specifically, I explored this Kaufman work. Well, it's not Kaufman, how it was, Spencer Brown
Oh god,
Wolfram, right?
we're
So
doing
basically-
lots of farm research.
Well, I've just it's like a small exercise. I basically represented it in Wolfram language so that you can compute it with it, maybe run some multi-computation with it, whatever. It's just basically the most difficult part of it is just do formatting, right? Because it's not really computing. You just specify a rule, you format it, and basically you have a nice computational object that you can just work. And besides that, also I looked into that iterant algebra. This is
Yes.
more Kaufman related thing, right? So I also represented it in Wolfram language, so you can also compute with it. You can basically this generalization of matrix algebra. So you can transform it into a matrix and back, and it has some nice number properties and algebra with it. So you can do this.
And just for some context for the reader, basically Nick is trying to escape from 1+1 dimensions. Life really sucks in 1+1 dimensions. It's even worse than flatland. It's
okay.
no, it's really bad. I mean,
In
all you
reality,
can
we
do-
all live in 1+1 dimensions. It just
life
those
on a
additional
world-
2 dimensions is just a completely. It's just it's an illusion.
Life
all
on
you
a
do
world
is just send signals back and forth. And so you don't know whether it's 3 or 4.
Well,
You
life on
just
a world line without the luxury of higher coordinates is not fun.
Yeah.
But as soon as you ask, how do we actually get these higher dimensions? It's not obvious. But Luke Kaufman, who's been kind of involved in our orbit for some time, um, has this particular algebraic approach that might be helpful. So you actually, but do you understand? I mean, I think one of the challenges is, I guess, making that functional, but then also relating it back to these anti-chain projections. Um, but
yeah,
maybe
just
that's
to
the next
tie it up
the next step.
conceptually. Here you have on one hand you have a nice algebra that you can compute things. On the other hand you have just autotheoretic object is a causal graph with just a bunch of relations between events, and you have observers, which kind of represented by a clock, just with some periodic thing on top of it. And this periodicity is what this algebra is trying to model, right?
About dimensions,
How, how does the periodicity give you the higher coordinatization? Boy, I'm
Well,
butchering that word. Coordinatization. It's really tough. Sorry. Anyway, how do you get the coordinates?
well, basically because if you just have two things iterating over and over, like A B A B A B A B, it's like tick-tocking clock doing a tick-tock iteration all over again. You can these two numbers, however you can assign numbers to both of those ticks, right? These numbers are naturally algebraically will form a diagonal of a matrix, right? Then if you kind of introduce an additional shift operator on top of it, it's like that. So, or arbitrary permutation in general. So iterant algebra is basically an algebra of permutations. It's a decomposition of arbitrary matrix in its permutation matrix components, whatever. But for 2 by 2 dimensions, it just requires one shift operator because it's either A B. If you shift it by 1, it's just B A B A, right? It's kind of represents the same sequence, but you don't know what is the started. It's like a shift, right? You shifted it, and if you so basically using the shift operator, you also can represent anti-diagonal of this matrix, right? So now you can so now you have like a whole matrix algebra by just this shift operator and this periodic thing.
But do the
But
two do the two additional entries in the off diagonal give you two different dimensions? Is that what the
yeah, that's
two
kind
by
of
two
where it
corresponds
is
to?
going. Yeah, so your
Yeah, okay.
diagonal kind of represents naturally this 1 + 1 dimensional world when you only have time and space, right? But this off diagonal is supposed to be represent the other 2 dimensions
Off time and
somehow.
off space. Okay.
Yeah, and it's naturally decomposes into a complex number also. Basically, or something that behaves like a complex imaginary unit, because I in this iterant algebra can be represented by just 1 minus 1, 1 minus 1 iteration. So shifted with
How
this
does
shift.
how does how does it relate to anti-chain projection?
Well, this I don't know. It is, because
Oh,
this
okay.
iterant algebra is just about how can you just quantify your event just using matrix or diagonal of diagonal hyperbolic and complex numbers. So it's just an algebra, maybe with some geometric interpretation, right? But how can you extract from the all the theoretic properties of a causal graph?
Yeah.
That's a different story. We kind of understand how to extract a diagonal, right? It's just basically if you represent your observer like a chain for your causal graph with a clock, right? You do this
Yes.
projections of events on this observer chain, and you extract this diagonal as iterant coordinates.
Those are the iterant coordinates. Yeah. Okay. Well, this is an interesting. This is promising. This is interesting. I mean, it sounds like a pretty concrete research question now to answer. How to relate this to your observer anti-chains. Well, I reached out to Lou. I reached out to him on Monday, not to put him on the spot or anything. He hasn't actually responded yet. This seems like a weird kind of week in that I'm guessing people are kind of recovering from having been away on holiday, and so they're kind of working through some pile of email. Anyway, so basically, Nick is planning the great escape from 1+1 dimensions, and Nick's been doing. Nick's kind of been one of the key leaders in really focusing on causal graphs for some time. I mean, I remember months ago, Nick would always question my interest in branchial graphs, for instance. And it's like, it's all just the causal graph. Everything's the causal graph. If you want to understand what one of these systems is doing, you basically just look at the causal graph. And but Nick has found you can also consider, branch-like relations within the causal graphs themselves. And this has led to this notion of anti-chain and anti-chains in causal graphs too. So this is kind of a unique kind of Mersonite idea.
Well, you can define
and
anti-chains without having any branchial relations. Its branchial relations are what allows you to do it constructively in some way.
well,
Right.
that's our style. Yeah.
Because otherwise branchial hypersurface is indistinguishable for usual Cauchy surface, space-like hypersurface, right? And there is no way to actually define an observer on top of that somehow. But well, you can do this. Maybe it's somehow related, and I don't know what this additional relation when we have an actual constructivism project on top of that, when we can say which events are space-like and which events are branch-like, whether it adds something new to that, right, or not. But conceptually, it seems like an observer can have an extension in space-like. Well, it can if you just allow more atoms, right, to occupy an observer. But elementary observer can exist, even be extended even without like being fat, right? A single atom of space can represent like an extended space-like observer too.
Yes, I mean,
It's kind of conceptual thing whether you want your observer to be spatially fat or branchially fat.
yeah, I mean, we've mentioned this before, but just for the benefit of people who haven't followed us in the past, I mean, one issue is that in special relativity, we do have like these notions of observers, which could just be literally like particles along a world line. And in our case, it's even worse because we have to construct our particles from things which are even lower level. So it's just one of these things on a world line, these things called eames on a world line. And it's like, that's where you begin in order to model observers. But I don't know what we'll call them, but they're basically like world line observers. Whereas what we need in our model are observers that actually perform observations. And it's kind of funny that that's like an additional criteria that you need to perform. But like it has to be an observer that has some computational sophistication, and you have to actually be able to explain why the observer is able to actually capture properties in the surrounding physical system, and what the observer is missing, what the observer isn't missing. So that's going to inevitably require some fatness because you need to be made of at least a few particles, presumably. And yeah,
at least for measuring these additional 2 dimensions, or have some quantum mechanical properties. Well, basically, we're trying to to abolish absolutism altogether. Like there is nothing absolute in this kind of picture. We're trying to model everything from an observer perspective. It's like general relativity, special relativity already abolished time and space as an absolute concept. But there is like things like motion is also we're trying to define it from observer perspective, not as an absolute thing. And there's no such thing as a manifold in discrete space too.
Sorry, Carlos.
Yeah. No. Sorry, I was just clearing my throat. I didn't mean to say.
No. I meant sorry because we don't have any smooth manifold.
Oh, yeah.
Yeah.
I mean, I paid this price a long time ago.
All right, cool. So yeah, that's what Nick is doing. Basically, building this stuff constructively all the way from the ground up, and that requires weird things like escape plans from 1+1 dimensions. All right, Carlos.
Yeah. So
how's the world below axiomatic mathematics?
Very interesting. So yeah, I've been mostly trying to implement the functionality we discussed last time and getting the function to work and so on. But I have also been thinking about our hypothesis. I think it was Nick's suggestion at some point. There was this bold claim that any random expression was going to encode something. So I'm going to try and be able to say something about that hypothesis next time. I am also, so I've been reading up on this laws of form thing, mostly because, to be honest, it looks to me like another candidate for this sort of subaxiomatic systems, right? At least in a traditional sense. There is a way to implement Boolean algebra with this laws of form thing.
Sure. Yeah.
And it seems very similarly minimal to SK combinator. So in some sense, I think there is something to be learned there. I think there is. These are very small. I still have to understand. Actually, have questions about the axioms. I don't know if we should use this time because we have questions that I think are interesting to discuss here in a group. But anyway,
yeah.
I've been thinking about that. I have actually met one of my sort of mathematician friends this morning, and he was curious about, what is your work at the institute now that is sort of more established and like you have more of an idea of what you're doing. And we had a very, very interesting conversation about subaxiomatic foundations. That's really what the name should be. That's one of those names that I think is very proper to what we are doing. And I know it was quite interesting to reflect on the fact that almost no mathematicians that I know of, and I have a fairly wide view of what people are doing, are really using this way of thinking, this rewrite mentality. There is small community of rewrite system focused people, mostly from a computer science background, and then there's some categorical flavor of rewrite systems that it's very technical. I don't have a lot of familiarity with the details of that stuff because it gets very technical, and that's about it. Then there's us, and then there's sort of the Wolfram sphere and us and whatever we're doing. So I find it very exciting. Like when I was explaining to him, which I think is a great thing to communicate here in the community forum, because in a way there's this sort of the localized community forum when I was talking to my friend explaining what we're doing, which is what I should be doing now to the audience, right? Explaining to the audience. So it was very illuminating to answer the question. So what is it that we are doing? And I was telling him, look, I think that what we at least what I am doing particularly with this project is really taking the tools of 20th century computation and try to do 19th century mathematics in some kind of way, and that's only possible in the 21st century. It's this kind of idea, because formal systems. I was having this hypothetical discussion of when did people realize that mathematics kind of boiled down to symbol manipulation, right? This certainly happened after the beginning of the 19th century, and surely before the beginning of the 20th century. So it's kind of bracketed within the 19th century. That someone, exactly who, I don't know if it's known or someone has a credit for knowing, for having the coming up with the idea of, actually this is just symbolic manipulation, and let's invent other symbolic systems that might do things for us. But certainly by the end of the 19th century and early 20th century, you have this formalist programs, and you have these people who just think that you just have a formal language and you have some grammars, and that's it. That's all you need. But certainly at some point, I like to speculate that maybe Lewis Carroll was sort of spearheading this kind of ideas, because he had very pioneering ideas about abstract mathematics and logic and whatnot. I like to think that some of these people were glimpsing at the fact that doing mathematics in a conventional way is mostly just rewriting. It's mostly taking term symbols and rewriting and applying rules and so on. So in a way, I like to think that what I am doing, particularly at the Institute with rewrite systems and developing these tools, is somehow the natural follow-up or the natural conclusion of this story that begins when we realized, oh wait, actually symbols themselves are meaningless, but it's how you make them into a system that's kind of a symbolic machine, that's really where you start to get some content of information. And to me, this is just the conclusion of that. It's like, okay, we have this massive stack of technology thanks to Wolfram research and Stephen's work, and we have all this research that's been done in computer science. And I feel like almost no one is really taking it super seriously. I mean, I know of some projects of like, the what's it called, the some chemistry focused rewrite systems and rewrite software that has been done, and all these projects for biochemistry as well and so on. But there isn't really that much, and those things were very focused to model stuff that happens in the world, like biology. But there weren't that many programs that were somehow trying to take this seriously as a starting point and then try to push the field forward. And I feel that that's part of what I think I'm doing. I mean, I think we are breaking new ground in just trying to. The way I explain to my friend how I work is that instead of a piece of paper and a pencil that you use to write your formulas, I mean, you spend some more time doing some code, and then essentially you have the same relationship with your code that you do with your pen and paper calculations, right? You do something, you look at something, it's like, right, so that's how it interacts. But instead of one step of rewrite that you can do in your head and then write down, it's maybe like thousands of steps, and there's a lot of stuff. And so I think I called it, I'm doing cyborg mathematics, because I sort of enhance my capacity to do mathematical reasoning and mathematical theorizing by computationally expanding those abilities. But in a sense, it's very purely mathematical, which is what I love. That I am doing mathematics. I'm not doing. They ask, oh, you deal with data science? You do machine learning? Do you do like no? I'm doing. It's fully computational, but it's all fully mathematical simultaneously. Right? It's great. So I think that's one sort of slogan that I would keep there. We are doing, at least in my project, I'm doing purely mathematical, but at the same time purely computational work, which is great. I think it's a good sign.
Yes, cyborg mathematics, and really trying to understand, as soon as you treat, say, Boolean algebra as a rewrite system, how at what level, at what kind of foundational level can you continue to emulate it, and at what point, does it continue to hold when you go down to lower and lower and lower levels? And really, what's the fundamental relationship between mathematics? Mathematical systems can be reduced down to axioms. Axioms can be reduced down to more and more simple rewrite systems. And is there a point at which, mathematics basically dissolves just into pure, kind of wild computation, or does the kind of ghost of mathematics kind of continue, to be recognizable at these lower and lower and lower levels of computation? So, yes, this is a question that you really, it's like going to these low levels, you really need these computational capabilities, because it becomes increasingly kind of inhuman, and it's not easy to follow. These combinator expressions are not at all easy.
You could even make the argument that the kinds of mathematics that we have. I mean, I guess Stephen would love this kind of conversation or this kind of argument, and some people have mentioned it before. But I think you could make the argument that the systems that we have, like Boolean algebra or the axioms of propositional logic or whatever, arithmetic, integer arithmetic or whatever, you could argue that these are axiom systems that have been selected out of the noise, the computational noise, that it's technically possible. I mean, nobody's stopping you from writing down the combinator axioms. I mean, they're not that complicated. I mean, there's just 2 rewrite rules that are, quite small. But why didn't we, stumble upon that and get using them? Because for just things like equals or implies or things like that, you need, tens of steps to derive more or less discernible results. I mean, maybe this is a bit of a cartoon, because I mean, in practice it probably won't work like that. But I mean, that's kind of the idea, that there might be a sense of natural selection of competing symbolic systems. That's kind of not true, because humans are very traditional, and we really have a theory. We don't have a theory of evolution of natural competition of formal systems. It's more about the accidents that happened along the way and how those things got improved and sort of put forward. But I mean, you can make the argument that there is a degree of that. I mean, the closer you are to human user level and human intelligibility, you're going to be, more common among humans. I mean, it's kind of a tautology to say that. And the more you stray away, the less intuitive. But from some purely mathematical point of view, or purely sort of computational point of view, these are equivalent systems. I mean, why should we? The only reason why we look at Boolean algebra and we think, oh yeah, this looks quite natural and important and fundamental, is because we think ourselves, we base our logic system on this stuff, and this is the abstracted version of our language and how we argue and debate and whatever. But we look at SK combinators or this law form or whatever other minimal computational system, and we see nothing. We see like a small piece of machinery that when it rewrites, actually it does stuff, and it's like, right, I don't know what that means. It's like looking at a molecule of like an amino acid and say, yeah, okay, sure, that's one molecule, and then you see an entire living being, and it's like, oh right. So it's not quite obvious that this unit will make this complicated protein complex things, right? So
yeah.
It's interesting.
That's why it's interesting, I think, to contrast what you're doing and what Łukasz is doing, because in part of why I'm interested in number theory is, I think the primes, for instance, this shows an example where we've created a somewhat neat, mathematical architecture as humans, but then there's still this kind of current, or these currents that run through it that seem much more irreducible or difficult to fully capture. And so I think part of the stakes for analytic number theory, including Riemann hypothesis, etc., is, can we gain a kind of epistemological control over the wildness of the primes just by building up higher and higher and higher abstractions, as opposed to this more kind of low-level effort of just kind of chasing the primes and just computing more and more of them. And is there some way where we can kind of outthink the primes? It's kind of a silly way of saying it, but can we kind of manage to kind of lasso them and kind of understand what they're doing just by building this very, very tall tower? And now Łukasz, basically without a harness, is climbing this very tall tower of abstraction. Yeah. Right. Well, great. Well, that was a fun summary. So
should we look at some of the questions?
Yeah. Let's answer some questions.
Okay. So I think there's a bit of hype in the chat about how I called the first question, which I dubbed it the axiomad. Because someone okay. So here's the question. So someone. Let me get the handle. Was it in comments? Where was it exactly? I want to get the handle. Sometimes I should get into the habit of copying the name, not only the questions. I mean, the question is, I found, it's Greg Palmer, of course. So the question is very simple. Is there a method to generate all possible axioms? And so he says, I've long been fascinated that we take a handful of axioms like piano axioms and outpops this infinite system of all the theorems and foundations of set theory or whatever. However, the piano axioms seem like just a subset of the set of all possible axioms. So I have been trying to think of ways to generate the full set. Is this what you're working at the subaxiomatic foundations? I mean, he was asking me specifically, and I answered in this sense yes, in this sense no. but I guess that we should address this question of, is there a method to generate all possible axioms? And in analogy with the rule version of this, I dubbed this the axiomad in the stream title, and people are, they're saying the axiomad sounds wild.
Well,
So-
I think they're right. I mean, okay, the way that we kind of set it up when Nick and I worked with Stephen on this is, you can define your axioms as certain rules. So you have a certain number of operators, maybe you have negation, but you're just defining this different kind of, you're just finding these rules that have different kind of levels of sophistication. And then your formal theory, et cetera, this will just be entailed from the axiom system that you set up. And so hypothetically, you can come up with all kinds of axiom systems. You could have a formal theory that basically is, A is equal to not A or something, and that will be a really wild, really quite unruly formal theory that you have on your hands. So, I mean, you can certainly begin to explore different kinds of axiom systems. And the real challenge is finding ones that seem to actually have rich behavior and aren't rife with contradictions. Basically, finding ones that are not inconsistent, for instance. So if you have A equals not A, that whole thing is just going to be rife. Even if there are other rules, that whole thing is going to be rife with inconsistencies. So, I would say, in order to...
We can just tell what we actually did in our mathematics book, in that axioms in the wild section.
Yes.
Right?
Yes.
What we did there is just, we took a simple binary operator. This is the only symbol that our axioms were allowed to take, right? And we can just enumerate those. And then we can just study all the axiom system. Well, we took just a single axiom of every form that you can construct with a single binary operator. And then we can just, starting from a single axiom with a binary operator, we can say what kind of theorems we can prove with this. Right?
Yeah. I think the one difficulty, though, is technically you can have... Well, I mean, is there an argument that really you should be able to express all axiom systems this way? Because, I mean, you could include multiple operators, and when we look at even
Why not?
if you look at Boolean algebra, for instance, it's quite complicated. You have at least two operators, you have negation, you have implication, et cetera, et cetera. But you could just do all that in terms of NAND, I guess. That would just be a single operator. But even
Well, at least
field theory,
at least constructive theories you can, right? Because as soon as you have something like exists, then you're already over. So you can just generatively use those kind of rules, turn those axiom equations
But you
into
can
rules.
you can treat exist just as formal symbol too.
Yeah, we do, but it's not gonna.
Rules.
Then you have to introduce other kind of axioms
Yeah.
that use the symbol.
yeah, I mean, it could become. It's
It depends
difficult.
how you treat it. You can, because usually your universal quantifier you can just treat as a variable in your rewriting rule, right? And all the existential quantified variables you can replace with a constant, and you just can turn it into a rule. But if you ask for some proof of some existential thing, you can't longer constructively make this proof using just rewriting rules, unless you also make them formal and add some other axioms and inference rules on top of that. Then maybe you can. Yeah. Well, you should be able to do this.
As for the question of enumerating all of them, I mean, there's just an infinite number of them. I think the more interesting question is not, can you enumerate all of them? Because you can't within your lifetime or your children's lifetime, etc. But the question is whether
you take binary operator and then you generate all the axioms. When you take two binary operators, you generate all of
It
axioms.
should be countable. I don't
Yeah,
think
it should be countable, yeah.
it's infinite, but it's countable. And basically, that's
you
all.
can enumerate it.
Yeah, enumeration is a question about countability. I think axioms certainly are countable.
But you'll never actually be able to see, like, what I mean is, okay, yes, it's countably infinite, but look, it's huge, guys. I mean, for practical purposes. What I mean is the more interesting question for practical purposes is you're only going to ever if you want to study arbitrary axiom systems, you're going to be able to study only some of them. It could be thousands, but thousands is pretty small compared to infinity. Um, and so I think the interesting question is, have we, as a species or what have you, as a civilization, have we missed important possible axiom systems? Because it's like, why should it be the case that, why should we presume that we found all the interesting ones? And so that's something, I would actually like that to be a, if I can find a way to scope that study so that it's not, this quixotic, an endless journey that doesn't go anywhere. If we can, if there is some nice way that we can do that, that might be a nice follow-up study for either some of our metamathematics fellows or future ones who come on board.
Yeah.
But it's like in addition to some axiomatic, it's also just other axiom systems and finding them. That'd be quite interesting.
I mean, to be honest, to add on that, because I was just thinking when I made my comment at the end of my synopsis. To me, I really see no conceptual difference between subaxiomatic and xeno-axiomatic in a way, or xeno-axiomatic, I guess. Because if you find an axiom system that, I mean, let me put it this way. In what sense is SK combinators not just another axiomatic system that happens to have those axioms and happens to not really care about what you make your statements about? You just look at the sort of rewrite structure of your expressions. I mean, it's just another axiomatic system. It's just that we have no motivation to write those particular rewrite rules, right? Those particular laws are very meaningless in themselves. However, all the laws, if you think about the axioms think of your favorite axiom system, right? And set theory or in algebra, some universal algebra stuff, take any of these axioms, you're going to, like, the popular ones, so to speak, the ones that are, used everywhere and, present in many different mathematical theories. These are extremely intuitive axioms, right? Like associativity, commutativity, distributivity, all these kinds of things. They have extremely natural interpretations in the real world, so to speak, right? Like
for us.
Yeah, for us, exactly. Yeah, for human users. So I always say the same thing, and it's great that you mentioned this xeno-axiomatics, right? Of going after other new axioms, the weird axioms. I've always said the same thing. Is like, okay, groups have happened to be this wonderful tool for fundamental physics in particular, right? Like symmetry and nature seems to know about representation theory of compact complex groups. It's like, what is this, right? Like, so groups have been this wonderful tool, and then what if 27 arity group-like objects had a much better way of encompassing what we observe in fundamental physics? What if that was the case, and a gauge theory based on these objects, for instance, was like everything for free, exactly the values that we observe in nature? Like, obviously, some people would say, yeah, that sounds like ridiculous because we are used to that not being the case. But I mean, who knows, right? Like, you really don't know. Who would have guessed that nature was going to know about SU3? I mean, I would have never guessed, right? Like, if I'm Maxwell, if I'm Maxwell in the late 19th century, and I'm doing my my differential equations, and they say, I come from the future, just 30, 40 years into the future, and look, there's this weird thing that mathematicians in Erlangen in Germany are doing, which is this complex geometry. And you know what? When you go deep enough in the nucleus, in the atomic nucleus, you need to know that to predict this. And nature kind of has these things baked in. that's absolutely insane, right? Like that's crazy to think about. So I think nature has proven us that these things are possible. Like these things just seem to be the case. So I mean, obviously, this is kind of an extreme to say something like 27 ARI group, but I think that you cannot know without really exploring these axiom systems, right? Like, it's impossible to know, and we have no way to really go into those realms without going statistically at them, right? Like let's list all possible axioms, let's do some large numbers of things and have random. And I think this is where our approach, as I was saying earlier, I think this is very unique, and we have a very unique opportunity to we can actually do mathematics on these higher levels because we can create our notational tools that are deeply or under the hood computational, but for user level, it's more like, I'm just doing computations or manipulations of symbols and so on. So I think this is super fascinating, and I would say that my project in sub-axiomatic foundations is really thematically is kind of in the same tank with this, right?
Yes.
It's very natural.
Yeah.
It's very exciting. I mean,
yes. I mean, that's
the
if we had kind of a factory of axiomatic systems, right? I mean, the outputs would be, yes, there'd be new kind of objects, not groups or fields or rings, but yeah, if you have these other formal theories, then there could be these other kinds of objects. Mm-hmm. I mean, yeah, I mean, new objects are of course created all the time. They just have someone's name, behind them. It'll be like the Mersenne functor or the Myshak space, or et cetera, right? But these are like fundamentally, special flavor. It's not like they're inventing ice cream. It's just like here's a particular kind of ice cream. Yeah. But of course, there are still more desserts to extend this metaphor. There's still more things that can be invented, and I mean, it does concern me that at some point these things were kind of proliferated, and now it's much more specialized, but there's no reason to presume that we've exhausted all the possibilities. Absolutely. And the fact that people don't seem to be intentionally trying to look for them suggests to me that we probably haven't exhausted them. If there was some program where at MIT or something, they had some supercomputer trying to come up with trying to find all the axiom system, then I would say, okay, fine. We've worked on this. We haven't found anything. We just happen to get lucky. Yeah. We happen to find all the good axiomatic, but it's unlikely. I don't think people are really thinking that way.
I mean, I can add because I mean this has been my research life for the last year and a half. I mean, there is a clear gap in the mathematical literature to understand these axioms that are not the ones that are common, and I think that even in category theory that you have this very abstract realm of people have done all manner of extensions and abstractions, going higher in different ways, in this homotopy sense, in this simplicial sense, and like all these ways of generalizing. Still, they rely on sort of either set theory as foundations, or at least conceptual foundations, or more conventional category theory as foundation, and therefore this transitive like properties and associativity if you interpret it more symbolically or algebraically, and so on. And what I find very interesting is that you actually find, I mean, it's a humble contribution to this axiomatic mathematics, but you kind of find this other axioms naturally when you go into realms of representation that are not typical. So, for example, when you break away from sequentiality in your writing, right? When we write everything in a sequence, it's some kind of string or whatever, tuple or whatever. So when you break away from that representation format or support, new axioms pop up automatically, right? And for example, we found something called heaps, which were invented algebraically in the 50s in the 20th century, but we just found them because we looked at a specific shape that look like an arrow going one way, an arrow going the opposite way, and then the arrow going the same way. So it's kind of a non-circulatory diagram that no category theorist would ever consider, because it's like, why would you do this? You cannot compose anything in this diagram. It's like a categorically sterile diagram, right? So an arrow like this, an arrow like that, and then an arrow to the other way. You cannot compose any of those arrows because they are facing in the wrong directions. But it so happens that if you take this pattern and you say, whenever you find this pattern, then you compose a full arrow. Then you have a theory of semi-hypoids, so-called semi-hypoids, but it's almost like groups. I mean, actually, you can prove that all groups actually define a semi-heap in this sense, and you know, and you have a theory of, I mean, it's very algebraically rich, and all you did is do something that to any common categorical eye would look sterile. So I'm just as a small example that I think there's proof that there is a great, you know, land of axioms that is unexplored out there, and yeah, we should go after them. I mean, it's
Yes.
great.
Well, so to viewers, people out there, if anyone wants to come and look for alternative or new axiomatic theories, if you wanna join, we probably won't begin this for some time, but maybe sometime in early mid 2023, we'll probably start it. So if people are interested in that, yeah, we should do this. Okay, well, that was a lovely question. Thank you, Greg. What else?
Okay, so
Besides consciousness questions,
yeah,
what
there was
else,
another
do we have?
question that I think came up the first week, if I remember, but it was asked again, and I think it was Greg Palmer again. Let me double check. Yes, it was Greg Palmer, and he says, "Have you developed any methods to tell if a system is computationally irreducible? Specifically, I work with molecular dynamics, which sometimes behave as complex, even chaotic systems, but sometimes it can be predictable. If there was a way to determine if the program needed to run to completion, or if a shortcut was available, could be extremely helpful."
Yes. So Jonathan wrote a paper called the slowdown theorem, which, at least as Jonathan describes it, is one of the first attempts to make kind of more precise in a mathematical and a computer scientific way exactly what irreducibility is. I'm not sure if Stephen ever produced a precise definition of irreducibility. I mean, when I look at some of the early papers like randomness in physical systems and undecidability and intractability in theoretical physics, are those the names of those two papers that Stephen wrote like in '84? Those papers are actually quite short, and they present like a classification of cellular automata, and they describe what autoplectic behavior is. I know that there were studies that were happening in the background where like Stephen was showing Rule 30 to Feynman, and people at Princeton were trying to crack it, and they didn't get anywhere. And it could be the case that I'm forgetting or I'm missing something. But Nick, do you know? Are there actual like tests for irreducibility? You know, that people have
No.
actually produced? No, I don't think there are.
I think that's besides the point. As soon as you have a test, it's no longer reducible.
Yeah, like the test would be irreducible itself.
Does that matter if the test is reducible though? Because
Well, it's that diagonal argument again, probably.
Yeah.
It's the same as Houghton problem. Right? You just make your diagonal argument and just do the same kind of conclusion.
it's always kind of troubled me that on the one hand, there's plenty of kind of anecdotal and experimental evidence that you see these formal systems that you simply can't predict. But I often speak about irreducibility, and in the back of my head, I think, well, what if it's the case that for this particular formal system, it actually happens to be reducible? Like it looks like a lot of these irreducible systems. And there's kind of culturally, we're kind of become accustomed to just thinking about this is irreducible, this is irreducible. But I do worry that there are like instances where something is actually perfectly reducible. It's just slightly reducible, and you need to run it for like 10,000 steps, and you can reduce
do
it
you
by
mean-
a few operations.
What do you mean by reducible and irreducible system? Like,
Well, what I mean is,
okay, let me say, like, every system is reducible and irreducible. Like, like in irreducible system, you could, for example, harvest some reducible. Like in principle, you could harvest some reducible behavior, maybe statistical or something. Like, I think in every system you could do that. But then you have
Defined
systems
using
that,
compressibility, right? How compressible is your output of your
yeah,
system or something like that? As soon as you
yeah, but
have to describe, in order to describe your system, you have to use the same number of bits as the system itself,
yeah,
and that's
but
the
I mean,
definition
to
of
define
reducibility.
to define reducibility, we use particular basis, let's say. So we have cellular automata which just goes 0 1 0 1 0 1 to infinity, and you say
Yes.
this is reducible
Yes.
because you're looking at it this way. But if you ask a question, what colors are on the consecutive prime numbers, this system is irreducible, and the other one is reducible. I mean, every system has some flavor of irreducibility and reducibility to it. Depends on the questions you ask. And for the system we call irreducible, we just don't know the questions. And for the system we call reducible, we just don't ask the hard questions.
Oh, you have to make it more formal than that. At least define what the system is doing, right? If you just have how is it defined formally? I can't really recall. Maybe something that takes like a process, something that takes an input of some size and outputs an output of other size, right? If this is the all that your system is doing, you can just by comparing sizes and how much and the size of your program that you're trying to describe this output for every input or something like that, you can define what your reducibility is, right? And if you
But
as soon as you make it formal, I think you don't have such problems.
But what about Lukash's point here that even for a checkerboard cellular automata to query the color of the if it's just if it's just like a two color CA, querying the colors for the prime number values
yeah, prime
that
are odd,
itself.
so maybe that's not a good example now
Well,
anymore. But
then your input is not. It's like you have to input your prime numbers or something. I don't know.
yeah, but
Right.
what if you just like you assume some sort of geometry in cellular automata, but you may as well simulate the same cellular automata in different geometry with different arrangement of your cells. And I think you can do that. You can make rules for that.
I don't know.
And then in this different arrangement, it would be totally irreducible.
I don't know. It still seems like you're just composing different kind of automata, right? If you're composing a reducible one with irreducible one, you obviously make an irreducible one. So as soon as you have a question that asks about prime numbers, which is irreducible question, and you compose it with a reducible one, then
Yeah, but
it makes it irreducible again.
if someone asks, if something asks about natural numbers like 1, 2, and so on, in this
Yeah.
order, then you call it reducible because that's the
Mhm.
system you work in, and you know natural numbers. So something that plays well with natural numbers, you call reducible. But how are natural numbers more natural than like you know what I mean?
But the other thing that concerns me is, at least speaking for myself, we don't know why there's irreducibility. But there was this thing called autocollectic behavior that this is like Stephen's initial description of irreducible computation. And this is some formal system that actually kind of produces more and more randomness or complexity over time. And it's like, I don't think any work has actually been done to try to explain why that happens. I mean, there's like, principle of computational equivalence, which is like this explanation that, you have irreducibility because no formal system is more sophisticated than another, and so you can't have one gain predictive power over the other one. But why is that? If that's the case, then why is that the case? I mean, I think that there probably is a kind of a deeper, especially once we start to model this kind of physically. It's like if we have with the physics project, for instance, if it's a fully constructivist effort and it's also supposed to be minimal from the constructor point of view, so we're trying to construct the desiderata for these different fundamental theories of physics. We're trying to do it with the simplest algorithms possible. But it's like many properties that we'll find in physical systems will be emergent. And so those will be explained via computational behavior. But if the computations are themselves irreducible, let's say, then this is like a kind of a fundamental property even of the constructivist dynamics. But I can't myself explain why it is that computations become irreducible. Have you guys ever thought about this?
I mean, my understanding of irreducibility is more from the other end of the sort of the spectrum of complexity. Is like any true computation is irreducible. That's kind of how I see it. It's like if it really is a fundamental computation, then it's irreducible, and it's when you sort of pattern over irreducible computations that you get reducible ones. Perhaps I'm just biased by the meaning of the words reducible and irreducible that I normally attribute to, and then I warped the concept to my understanding of computation, because that's what it sounds to me. I mean, and so far the explanations I've heard have been compatible with this image, right? That you have a composite computation, or otherwise indecomposable computation, right? Something that you cannot really detach from its parts to know what it is. But obviously, when you put it into the context of, for example, cellular automata, where very similarly looking rules produce completely different behavior in this sense of reducibility, right? Of something that, oh yeah, this has a pattern that can be reduced to always black here and this pattern, and you can specify and just extend to infinity that pattern. However, there are other rules, like, the ones that are random, or that have some patterns that you can only predict by random itself. To me, that just seems to me that it's like this is part of the world. Kind of that's how things are, and I don't know, like. It's kind of
I know, but that's the kind of scientific impulse, though, right? Which is you take these things that seem self-evident, self-explanatory, but you try and provide a more kind of verified explanation of it. I mean, yes, I mean most things are many things are not everything is reducible, but many things are reducible. As soon as you start to explore, I mean, we know this is we know this whole paradigm. As soon as you begin to explore these highly minimal rules, you find they have these kind of irreducible behavior. But why? It's such a naive, simple question.
If you think about it,
I realize.
Yeah, connecting to Łukasz's project and our discussions about Langlands and everything. I mean, primes are kind of an analogous phenomenon here, right? Like, in some sense, you set up your integers, which they are a very reducible structure in some sense, right? Like the integers themselves. I mean, you just need the first one and the successor. But then you define addition, which is, again, can be done only in terms of successor and the first one, and then you define multiplication, which again can be done in terms of addition, and then you set up the right question, which is divisibility, right? And then there's this prime pattern that appears in your numbers that is irreducible, in the sense that so far we haven't been able to reduce the problem of primality to just some kind of generative thing. So to me, that's obviously that property is not the property of the numbers themselves, and the numbers are completely reducible. Like the actual set of numbers is completely reducible. To me, that property is in the construction that you've put on top of it, right? The magic of the primes is in the construction of multiplication of natural numbers, and in the construction of the notion of divisibility and the question of divisibility. And so to me, that's how you're injecting the non-reducibility. And so that non-reducibility came from somewhere else, right? Came from
you ask sort of question that is irreducible in respect to irreducible system. You get system that goes 1, 2, 3, 4,
Yeah,
just goes
yeah.
this linear way, and you ask some question that is irreducible. But yeah, it may be perfectly reducible question in the other system. Like, I think we should define irreducibility with respect to some basis that we
Yeah.
used to
Yeah,
discuss.
I think reducibility. I think that's why I said that I go the other way, right? Like I think that what is fundamental is irreducible, and then the composite is reducible, because you know what's irreducible in the integers is the first element and the successor function, right? I mean,
Right, and if that's all
And
that number theory was, it would be super boring.
exactly,
Right? If it was just successor, or even if it was just addition and its inverse, it would still be quite boring.
Yeah,
I mean, the
correct.
explanation that I've kind of given, but I still fear that it's somewhat of a that it's still too simple of an explanation. Explanation that I usually give is I refer to the primes, and I would say, if you have some formal system, and um, when you consider only its kind of primal building blocks, if those have kind of rich, unpredictable behavior, then the overall system will have this richness too. If it's the case that when you break it down to its fundamentals, if those fundamentals are highly reducible to something very, very simple, then the overall system can be too, and it's not terribly rich so it's kind of this richness argument, and this probably leads to things like anthropics, et cetera, et cetera. That if we were in some universe that could all be kind of compressed down to 42, then it might not host the requisite richness, to be able to support us, et cetera, et cetera. But this seems, there's some relationship probably between primality and anthropics and irreducibility, but it's still, I never love those arguments, which is like things are the way that they are because, if they were different, then we wouldn't exist. And I never loved those kinds of arguments, to be honest.
To me, they are not
'Cause it
arguments.
doesn't-
They are things you tell yourself to go to sleep.
Like, I mean, are natural numbers irreducible? Like, let's say you have additive group of integers.
Yeah.
Like, everyone here would say that it's pretty reducible behavior. But then you can ask the question about primes. You can make the definition of multiplication the sort of part of your question. If you
that's
repeat that
that's
they
what
can
Carlos.
go on,
When you allow questions, you also kind of
Yeah,
add another formal system, which is
Yeah,
logic to your numbers,
then-
and that makes natural numbers reducible.
yeah, but then you say the irreducibility is in the question. But then I'd say that you define reducible behavior as something similar to integers.
Yeah.
Like, if you define reducibility is defined as expressible by integers and arithmetic and so on. If you can find formula involving these things, you coordinate your abstract space in some integers, and then you want to use arithmetic and you want to find formula. If there exists an easy formula, then you say that it is reducible. But it is sort of reducible by definition, because if you change your entire setting, then may exist easy formula for the behavior we would call irreducible in that setting. And for example, addition of natural numbers would be totally unnatural and would require many levels of abstraction.
But at the same time, I think, we use this tool, right? For example, in traditional set theory, countability is exactly that sort of pattern, right? Where you're sort of measuring your things based on, can I find a bijection to the construction of the naturals? There's this successor function, right? So I think that we do that. I think that, but to say that reducibility should be just based on natural numbers might be a little bit restrictive. It's better to say, I think.
No, but like in practice, it is now. We call reducible behavior something that we can find an easy formula for.
Yeah, I mean, you're probably I would actually agree that in practice we are, the way I've heard this term being used is that
Yeah.
when you can find a formula that is effectively doing integer arithmetic, so some sophisticated successor function on an initial element.
I think you can quantify it like that. If you ask a question of natural numbers have this natural quantity assigned to them, which scales with the actual number, right? So the bigger the number, the harder the questions becomes. Any question you can ask about, right? And if the question is whatever question you ask of natural numbers and ask whether it's reducible, has an irreducible answer to it or not, it's basically can be quantified like that. It's reducible when wherever you scale your input, you have like some upper bound to it, right? But if it continues to scale with your input, the amount of computation you have to do in order to answer it, then it's irreducible. But as soon as it has upper bound, then it's reducible. So this is like maybe this is more formal definition of that.
Mhm. Okay.
Something else. Something else maybe we can discuss briefly is, I think this comes up. Well, maybe this relates to each of the projects that each of you is working on. I mean, one issue is that, so there are people who basically just study irreducible formal systems. Like they'll just literally just study cellular automata, or they'll study, different rewrite systems, or they'll study, diffusion limited aggregation, or what have you, right? And you could spend a whole career studying their statistical properties, running them, et cetera, kind of like MKS. What we're doing, each of the projects that we have, they're slightly different. Carlos's is very experimental. Nick's is basically constructivist, and Łukasz's is basically translative. I mean, they're all kind of slightly different. They're making use of different things you can do with computation. Actually, ultimately, Łukasz's is right now translative, but eventually it will be trying to. It's not making it. I guess I would call it translative in the sense that Łukasz is not constructing Langlands. God forbid he tries to construct Langlands from Turing machines or some shit like that. But he's also not But he's also not running experiments with Langlands, at least not yet. But at some point, it will be: can you translate enough of this into computation so that you can start to do aspects of it computationally in an efficient and helpful way? So each of you encounters irreducibility. I mean, Carlos just gets smacked in the face with irreducibility when it comes to these SK combinators. Nick, not exactly sure how much irreducibility Nick encounters, but if we actually start generating causal graphs from random underlying rewrites, then yes. And in Łukasz's case, I mean, I guess this kind of battle with the primes is also somewhat similar. But in some sense, with Carlos, it's like the behavior of the SK combinators could just ultimately be not only irreducible, but irreducible, and to such an extent that you can't actually recover any the Boolean operators in the emulation, even if they're there. And so in some sense, with Carlos, it's like, we're trying to actually assess to what degree irreducibility poses this kind of effective computational barrier between mathematics and kind of underlying computation, where at some point you just kind of lose track of mathematics because it becomes so difficult to follow at this underlying system. Now, I would kind of like it to be the case that you can always continue to chase the kind of ghost of Boolean algebra further and further and further. At least that's what I would like to see. And so in some sense, what Carlos is doing is purely experimental, but irreducibility is somewhat of a, it's like this Faustian bargain, which is the more minimal you get, the more irreducibility there is. And trying to understand at this very low level things that we actually care about. Can we still kind of extract them from that, or do we just kind of lose them? And so in this sense, irreducibility is kind of this unfortunate thing. I'm not sure if irreducibility is kind of good or bad in Nick's work, and it's not clear to me if it makes things easier or worse, or if it's kind of irrelevant when you're constructing things. I mean, one thing that I do worry about is like in Nick's case, let's say we try and start to construct the standard model from these low level foundations. Or let's say we address some question like the cosmological
That's
problem.
standard model construction is not really in our nature here. That's the job
Why
of
not?
grand unified theories, right? As soon as they construct it, you just can't borrow it.
No,
That's
but
not our problem. Foundation.
well, I don't think we're going to get very far in the physics project if we can't construct different particles that have the right properties. Like eventually we'll need to be able to have some definition of angular momentum and energy and mass, etc., and then be able to actually find
Physical
particles.
quantities, yeah, okay, but what kind of symmetries they satisfy, and so that they actually reproduce the actual physics that we observe. I don't think that's not what we should focus on, right? Because the actual studies of symmetries, I think there are already other groups and people that are doing that. That's the grand unified theory approach, right? To actually construct the nice symmetry that reproduces the actual particle physics that we observe. Right?
Well, okay. One
Not
step at a time.
reconstruct it from just all the theoretic properties of a causal graph.
Well, let's just say, let's just take the example of trying to find like particular, leptons or something. Like we're trying to actually construct particles. I mean, or we can forget about the particle. We can just say, let's say we're trying to address, some difficult problem in fundamental physics, like the hierarchy problem, or a question of dark matter, or these different questions. One of the difficulties is that if we're going to if we just literally emulate existing physics from computational foundations, that is, what do we gain by doing that? Well, we can say our models are more minimal, they're more parsimonious, we've constructed everything, et cetera, but that only goes so far. At some point, you want to have this rich constructivist architecture, but you want to find things that are new. And I think irreducibility does, on the one hand, it makes it possible to find things are new because you're at this low level and there are these dynamics and you're trying to interpret them and make sense of them. So that's kind of why you do things from a constructivist framework, because you're taking advantage of the rich dynamics of the underlying computation by going more minimal. But on the other hand, I think it's going to be very difficult because we're going to find all kinds of shit when we're operating at this low level. And it's like trying to interpret this weird effect. This weird effect. Is it just, this is a bad computational sample? We're trying all these different computational samples. Not all these rules are going to give rise to things that are recognizable in physics. So, this is like Nick and I are discussing this whole question of, you have these underlying data structures that have fractional dimensions. What do you make of the fact that we have underlying data structures that have fractional dimensions? Right? There are kind of two conclusions. One is, well, this is obviously not the right sample because our universe doesn't have fractional dimensions. Or, oh, maybe our universe does have fractional dimensions and this sample is correct. And we're going to hit those kinds of epistemological questions, I think, quite often. That we'll model something and it's like, is this a weird anomaly and we should just disregard this sample? Can we explain this? And is it in fact the case that if you interpret it the right way, that this particular property of the model actually gives us something familiar? Or is it the case that we found something that's both valid and important but unusual, and we should actually propose a modification to some aspect of some theory because we have found some new behavior in the model? And when we're dealing with questions that are wide open, like cosmological concept problem, it's like we do want to find novel, rich, important features in our model that can make some contribution. But trying to discriminate that, but trying to discriminate that from underlying junk or just random kind of behavior in our models, I think is going to be really tough. So I'm just
Modeling things and trying to find some predictable properties of those is kind of last part of this. We haven't finalized our conceptual ideas of how
No, I
actually
agree.
that's what we are lacking mostly, right? Because we
Yes,
can't even ask questions. How can we study models if we can't even ask questions of our models?
I agree. I agree. I agree. I have I have these discussions with Stephen too, where I say the same thing, where Stephen is talking about, doing experiments. We should start doing some experiments to test different aspects of the physics project. And it's like we can't even pose hypotheses yet. Because like we don't have enough of even the properties or the objects or the aspects of these formal theories that are not even specified yet. So it's like we don't even have, I think, this isn't strong enough to even be able to ask these kind of questions. And Nick's making the even more modest point, which is even from the modeling standpoint, it's not clear what to look for yet. That's why Nick is doing exactly what Nick is doing, which is like going back to the very beginning, and it's like getting a nice way to extract energy values, momentum values. We haven't even done mass yet. It's like when you go all the way to the bottom, you have to define all these things from scratch, and they were kind of provisionally described in like 2 years ago, and people really didn't work on that much. People kind of took that and then started doing kind of higher level things from it. But it's like, this is what you actually have to do. If you're going to have a constructive model of physics, you have to literally construct every single aspect of it and kind of build it up. Anyway, I'm just thinking through like how irreducibility relates to these different projects. And it does. But the problem is in every case, it's like kind of a bad thing. Like we don't, it's like, there's this kind of poetic justice to it. And on the one hand, you need it. Carlos needs it, or you end up getting it because of choices that you make. If you dance with combinators, you're gonna get hit with irreducibility. If you construct things from a low level, you're gonna get hit with irreducibility. And if you start to play around with the primes, you're gonna get hit with irreducibility too. So it's like, I don't know. There's something poetic about all of this. It's like you want to hate it, but you also need it.
Indeed. I think it's a good closing note.
Are we done?
We are beyond done. Yeah, over 30 minutes almost.
Oh wow. Well, I feel like I just spoke a lot. I don't want to end with just some monologue. Is there maybe is there one other question that you guys want to take a crack at maybe more briefly before we wrap? I feel
Sure.
like
There was
spoke quite a bit.
Let me bring one from the chat. I think there was one in the chat up here. So, I mean, this is going back to our previous question about the axiomat, but someone asked, Prutz asked, the axiomat should be somewhere within the Rulliad, right? So, yes, short answer.
I mean, you could ask whether or not they're equivalent.
And this was another good point made by Ettore Mariotti. Doesn't reducibility come from computational boundedness of the observer?
Well, the computational boundedness of the observer makes everything irreducible, even actual reducible.
Well, that's a good question. The point there is, if you don't even have the computational sophistication to be able to gain predictive power over some formal system, then absolutely that system is going to appear to be irreducible. So I suppose irreducibility always involves an observer, or it almost relates to the stuff Nick is doing. Like it's always a comparison. You have some underlying computation, and then the question is, is there another computation that can compress it or can predict what the subsequent behavior of that is going to be. And so, this is basically why Stephen arrived at this computational equivalence principle, is you always need at least two computations in order to pose the question of irreducibility. And I think Stephen's point is, if irreducibility is pervasive, then it means that basically in most cases, given two computations, one computation won't be able to compress the other. And so they have some equivalent degree of computational sophistication. But it still bothers me that I don't understand exactly what that kind of computational sophistication is, like what it actually means. Like it's always been kind of just described as, they're both similarly computationally sophisticated, so one can't gain any traction over the other. But it's still this kind of deeper question of what exactly is computational sophistication, and what exactly is this property of irreducibility in a deeper sense. And it's like, it might sound silly to ask that question because it's like it might not be possible to explain it, but it still does bug me. I remember when I first learned about this, I thought, well, why is this the case? Why is it the case that these kind of systems can just be irreducible? Wait, this wasn't supposed to be. I wasn't supposed to answer this. This was supposed to be someone else.
I think Nick started the answer, so technically we're safe.
Yeah, you just expanded on it a little bit.
Exactly. So we're good questions and good chatting in the chat, actually. Thanks, Ettore, Brutz, who else was there? Asa, I think, was around at some point. Yeah, thanks for your comments. It's a lively chat.
Yeah, and for those on the chat, if you're not part of the Discord, feel free to join. Once again, if you go to the community page, wolframinstitute.org/community. I'll just post it here. Oh, okay. Someone beat me to it. Yeah, you can join the Discord and ask all kind of questions that you have, and we'll answer them either there or here. Mm-hmm. Well, hey guys, this was fun. I always look forward to these. All right, well, see you. See you guys tomorrow.
Can
Cheers.
we stay for 2 minutes after this? After we go offline?
Yeah.
All right, everyone in chat. Thank you for your comments.
Bye, everyone.
See ya.